Introduction to Neural Networks with C#, Class 4, Part 5. Welcome to Part 5. In this part, you're going to learn about the backpropagation algorithm. We will look at the backpropagation algorithm both at a mathematical level and see the C# classes that are necessary to implement it. This book provides classes that train the neural networks in a backpropagation technique. In this class session, we will peer inside of these classes and see how it actually happens. Later chapters will introduce other more advanced neural network techniques that build upon this, and they will make use of these classes. So it is important you understand how they work now. We will begin by looking at the backpropagation algorithm at a mathematical level. There's really two steps in backpropagation. First, you calculate the error contributions. Once you've calculated the error contributions, then you adjust the weights to minimize the error contributions. What do I mean by error contributions? Backpropagation works backwards. You start with the output layer, you calculate the error that the output layer has produced, and then you go one step further. You determine how much each neuron, according to its weight, has contributed to the error. The neurons with the higher weights contribute more, so they will need to be adjusted more. Then you work your way to the next layer, one of the hidden layers, or perhaps the input layer, and you determine the contribution of that layer to the error going to the next layer. You keep working your way backwards and adjusting each layer's contribution to the error to the next one until you've worked your way all the way back to the input layer. This is all accomplished in a function called iteration that is provided by the backpropagation class. As its name implies, you don't simply call iteration once. You call it many, many times. Each time that you call iteration, it improves the error by some degree. Let's look at how iteration actually works. It loops across all of the input sets. These are the training sets. For each training set that it loops over, it calls calculate outputs. So it actually runs that against the neural network and sees what the output is. Then it calls calculate error. And notice it calculates the error based on an ideal set. The ideal set was provided with the inputs. This is what we expected it to be out. Backpropagation is supervised learning. So we are providing the ideal values that we expect for each of the inputs. Once we have finished looping over all of the error sets, it's time to call the learn function. We're going to look at the learn function a lot more closely in a moment. It is the second phase of backpropagation. It actually modifies the weight matrices based on the errors that were determined as we looped over the training sets. Then you see that we update the global error. This is the error of how close this set, this neural network in its current state, performs given all of the training sets. This is the number that was displayed when we ran the XOR problem. This is the error at any point after an iteration has been called. It is necessary to calculate this error so that we know how good we're doing, and we may decide to stop once the error reaches a certain level. Again, this is the iteration function, and this continues until it is trained satisfactorily. Now let's look at how the error contributions are actually done. Here you can see that we're looping over all of the layers. But look at the for loop in the top line. It's looping backwards. This is because we're doing backpropagation where we want to consider the output layer first. One by one, we obtain the layer and place it in a layer variable. We call one of two different calc error functions. We need one error function for the output layer because it's handled differently. We'll get to what that difference is in a moment when we actually look at it. If it's an individual layer, then we simply call the calculate error that does not pass in the ideal. This second calculate error is simply going to look at the next outer layer to determine how what its contribution was. This process continues from the output layer all the way to the input layer until all errors across the network have been calculated. Now let's look at how we calculate the error for the output layer. You can see that we're passing in the ideal values. We're going to loop over all of the neurons in this output layer because we want to see the contribution of each of these neurons to the actual error. We're going to set the error for this neuron by calculating the difference between the ideal and how it actually fired. Then we're going to calculate the error delta. The error delta is what is going to actually change when we get around to actually learning how to update this layer. Let's see how that delta is calculated. Here we multiply the error by the derivative of the activation function passed in the amount that the neural network fired on. This is really the heart of the backpropagation algorithm. We use these derivatives to calculate the contribution of each neuron to the error, and this gives us a delta that is going to be applied to the neuron's weight later when we actually update the weight matrices. The delta is the amount that we need to change the neuron's weight by to achieve this change. Now let's look at how we calculate the error for each of the layers other than the output layer. This is a little more complicated. Notice the two for loops at the top. We are looping through the matrix in a nested manner. This hits every row and column of the matrix. Then we're going to accumulate matrix deltas. We are looping, as we're looping over each of these values, we are determining the error delta just like we did before, and we're also setting the error for each of these neurons as we go through and calculate this. We also accumulate bias deltas, which is very similar to the other deltas, except they are going to be applied to the thresholds. As we loop through all of these values in the matrix, we build up our list of deltas so that we have the numbers that we want to change the weight matrix by when we actually learn. Finally, the learn method is called to actually perform the updates to the weight matrix. By this time, we've already done all the heavy lifting. We've created this array of delta values that is going to be applied to the matrix. Now all we have to do is apply it to the matrix. We begin by looping over all of the layers. For each of those layers, we are simply going to call the learn method with the learning rate and the momentum. The learning rate and momentum are actually applied here. Learning rate is how fast we want to actually change these values, how strongly we want to apply the deltas. Momentum allows learning from the previous iteration to affect the current iteration, and to what degree we want that. 0, no degree, or 1, completely influence it. This helps the neural network to not get stuck in certain learning instances. And here we see how we update the weight matrix. You notice that you have M1 and M2. M1 holds the effect that the deltas are going to have on the weight matrix. M2, you can see that M1 is calculated by multiplying the deltas that we previously calculated by the learn rate. You can see that M2 determines the amount of effect that matrix delta, which is previous learning iteration, is going to have. This is when you add these two together and then actually add it to the weight matrix. You can see that we assign the result of this multiplication to matrix data. This allows us to hold it. Determining the values for learning rate and momentum can be difficult and usually involves some trial and error. This concludes class session 4. In this class session, you learned about the feed-forward neural network and the backpropagation training algorithm. You also saw how activation functions were used and hidden layers, how they were applied to feed-forward neural networks. In the next section, we're going to see another way that feed-forward neural networks can be trained. We hope you will continue on with class session 5. Thank you. This course is based on our Introduction to Neural Network Programming books for Java and also Introduction to Neural Networks for C#. Available in both paperback and ebook format.